Okay, the last thing in our main discussion of sequences and series is this idea of summing to infinity. So, first of all, what does that mean? Well, it means if we just take a simple arithmetic sequence, 3, 5, 7, 9, and so on, we're used to having a certain amount of values. We're used to having a sequence with 80 values in it, or 100 or 120. But theoretically, this sequence can continue on forever. I can keep adding 2 to the sequence for infinity. So, what happens if I want to keep adding these numbers together for an infinite amount of times? 3 plus 5 plus 7 plus 9 plus 11 plus 13 over and over and over again to infinity. Well, you might say, well, the answer is clearly infinite. If I keep adding numbers together, it's going to get larger and larger and larger. It's going to become infinite. And you are correct, but only some of the time. To understand this, we're going to need to understand the difference between what we mean by converging and what we mean by diverging. So, if a sequence or a function is diverging, we'll start with, it's more or less what we just looked at. A diverging sequence would be something like 3 plus 5 plus 7 plus 9 plus 11 adding together infinitely. This is diverging because no matter what, as we keep adding numbers together, our number will get bigger. Every time we add a number to itself, it will get bigger, and it will get bigger faster. Eventually, we'll be adding millions to millions to millions to millions, up by 2 every time. Because of this, we can't really add these things together. Okay, we end up with a diverging sequence. So this here, we would probably just say is infinity and leave it alone. Converging, on the other hand, let's take a geometric sequence. Starting with a half, well actually I'm going to start with 1. Starting with 1 and adding a half, and then a quarter, and then an eighth, and then a 16th, so on and so forth. Now, what I notice here, and this is a geometric sequence with r equals a half, I'm multiplying by half every time, is if I keep adding these together forever, and I encourage you to put this into your calculator and give it a go. If I keep adding these together forever, it won't necessarily hit infinity. Now, if we go a couple of years ahead of schedule with this, we'll see that, sometimes it technically does, but that's, above the pay grade at the minute. For now, I just want us to have a look at a simple sequence like this and put it into the calculator. 1 plus a half, right, well that's going to be 1.5, plus a quarter, 1.75, plus an eighth, what's that, 1.0125, so 1.875, plus a 16th, no chance doing that in my head, and so on and so on and so on. If we keep putting this into a calculator, what we'll notice is eventually the calculator will tell me the answer is 2. And no matter what I add, probably by that point we're talking about in the thousands, I would imagine, depending on when your calculator starts rounding, it's going to tell us that if we add all these numbers together, forever, it will round to 2. And this here is a converging sequence or series. No matter how much we add together, we are going to end up converging and coming into one point, and in this case, 2. So how do we prove this using an equation? Okay, I'm going to start off with my sum of n numbers in a geometric sequence. The reason I'm doing a geometric sequence, as I kind of alluded to earlier, is that an arithmetic sequence will never be convergent, or an arithmetic series will never be convergent. Because no matter what's going on in my arithmetic series, my numbers are always going to be getting either continuously larger or continuously smaller. Either it will be, 5, 10, 15, 20, and so on, or going backwards, 5, 0, -5, -10, etc. We're never going to converge on a point. Even here, where, I'm minusing Out of 5 plus 0 is 5, minus 5 is 0, but then I start doing minus 10, minus 15, minus 20, I'll end up at minus infinity, more or less. So we never want to be thinking about an arithmetic sequence here. So let's concentrate on our geometric. And let's replace this n with an infinity. I'm no longer summing just n items, I'm now summing an infinite number of items. And what I'm going to do is I'm going to pop that infinity into my n here, or I will keep doing that in red, not to steal the other guy's thing. Okay, now how do I deal with this? Well, I'm going to need to take some limits. And I will show you what I mean by that if you are unfamiliar. But if you're following this along as an A-level course, you should be familiar from first year, year 12. First thing I want to note is I have got two possibilities. Once where the modulus of r is less than 1, so that can take any number between minus 1 and 1, so it is a fraction. Or I've got when the modulus of r is greater than 1. So, because I've got the modulus, this includes negative numbers, so negative 2, plus 4, negative 18, plus 104, something like that. Now, I'm going to start with this one first. If r is greater than 1, then in my sequence, every time my number will be getting bigger. So, for example, if my r was 3, and I start with 3, my next number will be 9, my next number will be 9 times 3 is 27, and so on. If my r is greater than 1, my sequence will keep including larger and larger numbers, and if I try and add them together, it will diverge. So when the modulus of r is greater than 1, no bueno, not going to happen. I can't sum to infinity, I'm going to get a diverging sequence. But when r is less than 1, as I showed earlier, if it's a fraction, so for example a half, or I'll do a third because I did a half earlier, if I start with 1, my next number will be a third, my next number will be a ninth, my next number will be a 27th, and so on. And in this case, my numbers are getting smaller every time. So when I add them, they will converge. And I showed this earlier with having r as a half, it keeps going until it converges to 2. So, first thing to note is it only works, this whole thing, sum to infinity, only works if the modulus of r is less than 1. So, let's put that together and have a look here. I'm now going to rewrite this equation using a limit. The reason I'm using a limit is because I can't technically just throw an infinity into an equation. Maths doesn't allow that. So instead, I'm going to say, as n approaches infinity, what happens to a of 1 minus rn over 1 minus r? Well, remember, r is a fraction. I'm just going to divide that off. R is a fraction. So what happens as I raise a fraction to an infinite number of powers? Well, if we play around with it, again, I'll use a half because it's the easiest example and it's the one I can do in my head, more or less. A half squared is a quarter. A half cubed is an eighth. A half to the 4 is a 16th. And as my power gets larger and larger, my number gets smaller and smaller. So I can say that as n approaches infinity, r to the n approaches 0. It gets smaller and smaller and smaller. Now, it never reaches 0, but technically n also never reaches infinity, because that is a mathematical impossibility. So, if r to the n has tended to 0, then s of infinity is going to be a times 1 minus 0, which is 1, which is just a, over 1 minus r. And this here is my equation to sum all the numbers in a sequence up to infinity.